Welcome to this video on the quantum mechanics of non-radiative decay. We will navigate from the Schrödinger equation to understand the physical limits of near-infrared emitters. There is no single simple non-radiative decay law. The exact law is the time-dependent Schrödinger equation for the coupled electronic nuclear wave function, involving the full vibronic wave function and Hamiltonian. Decay is driven by imperfect separation. Non-radiative decay happens because electronic and nuclear motions are not perfectly separable. Population leaks occur between electronic manifolds as nuclei move. Fermi's golden rule, or FGR, bridges theory and calculation. When interstate coupling is weak, FGR becomes the practical rate law for evaluating radiative, IC, and ISC rates. The skeleton key of non-radiative loss, or KNR, is proportional to the square of the coupling strength multiplied by the density of final states. A tiny operator can have massive consequences. The standard intrinsic enemies of organic emitters are internal conversion, IC, and intersystem crossing, ISC. Both are typically evaluated within FGR frameworks, provided the weak coupling approximation holds valid. Conical intersections act as a molecular trapdoor. The Born-Oppenheimer approximation collapses locally. Electronic and nuclear motions become strongly coupled, making decay ultra-fast. Energy is dumped before emitting. The energy gap law is an emergent consequence. The non-radiative rate grows roughly exponentially as the electronic gap gets smaller. This is a consequence of FGR plus vibronic overlap structure in polyatomic molecules. The quantum reason behind the shrinking gap is that the electronic energy gap must be dumped into vibrations. A smaller gap needs fewer vibrational quanta, leading to a larger overlap and higher decay rate. Modern nuance shows it is not just CH stretches. The dominant IC pathway can arise from first derivative non-adiabatic couplings involving multiple Frank-Condon modes. Skeletal modes play a critical role. Deuteration only provides modest changes in some NIR systems. Skeletal modes play a critical role. Treating the issue as just single highest frequency CH stretch folklore is chemically lazy. Near-infrared, NIR, emitters are intrinsically hard. Redshifting hurts you twice, as it alters both halves of the quantum yield equation simultaneously. The quantum yield, phi-PL, depends on the radiative and non-radiative rates. You are mugged by quantum statistics and electrodynamics. As emission frequency gets smaller, the radiative channel weakens with the cube of the frequency, and the non-radiative rate increases due to the energy gap law. The architecture of non-radiative decay moves from the fundamental truth of the Schrödinger equation to the practical model of FGR, the loss mechanisms, the emergent heuristic of the energy gap law, and finally, the engineering reality of the NIR curse. This video is about the quantum mechanical design of high PLQY NIR emitters, focusing on a first principles blueprint for engineering the molecular Hamiltonian. The true objective is not simply to make it redder. The photoluminescence quantum yield, phi-PL, is the ratio of the radiative rate to the sum of all rate constants. We aim to maximize the target engine, the radiative rate K_R, and minimize the leakage channels, which include non-radiative rates. Step 1 of the quantum engine is determining stationary points and energies. We calculate the adiabatic E00, vertical excitations, and relative state energies. The method selection depends on the molecular character, ranging from TDDFT for bright organics to multi-reference methods for diradical character. Step 2 involves computing modes and displacements. We extract mode-resolved Huang-Riesz factors to find the reorganization energy, lambda. A large lambda signifies stronger electron-phonon coupling and worse non-radiative behavior, so lowering lambda is critical for emitter design. Step 3 focuses on coupling operators, internal conversion, IC, and intersystem crossing, ISC. We compute non-adiabatic derivative couplings for IC and spin-orbit matrix elements for ISC. First principles methods for these are standard for weak coupling cases. Step 4 is evaluating the rates. Instead of the complex explicit vibronic sum, we use the thermal vibration correlation function, or TVCF, formalism. TVCF is the preferred method for predicting radiative and non-radiative decay rates from first principles. Step 5 addresses molecular chaos, especially if a conical intersection is accessible. If the barrier to the crossing seam is low, the harmonic Fermi golden rule is abandoned, and explicit non-adiabatic dynamics methods are deployed. Rule 1 is to minimize reorganization energy lambda by engineering rigid frameworks and compact excitations. Rule 2 is to keep the oscillator strength large, preventing vanishing transition dipoles, which is necessary to fight the collapsing radiative rate in the NIR region. Rule 3 is blocking the crossing seam. Bond twisting or excited state charge separation can lead to non-radiative decay via conical intersections. The solution is using conformational locking and fused rings to remove low-energy access to these intersections. Rule 4 is identifying the guilty vibrations. It is a myth that blind isotopic substitution always fixes non-radiative decay. Skeletal modes often dominate the non-radiative decay. The protocol is to compute mode-resolved calculations and structurally modify only the specific guilty vibrations. Rule 5 involves engineering excitant delocalization to reduce electron-phonon coupling. Rule 6 is controlling aggregation quenching separately. For NIR, active packing control is often required to attenuate the energy gap penalty without causing quenching. The architect's blueprint is a 6-step workflow, from selecting a rigid core and ensuring a meaningful transition dipole moment, to redesigning dominant modes, raising the energy of conical intersections, controlling aggregation, and finally, recomputing all rates. The quantum game in one sentence is to engineer the Hamiltonian so the excited state amplitude has nowhere cheap to leak except into light. This means simultaneously keeping the radiative dipole large, reducing reorganization energy, weakening non-adiabatic couplings, and eliminating access to conical intersections.